Okay, we're back. We're now looking at the receiver.
So there are two coils here, right?
This was a mod that I did.
Yeah, yeah.
All right. So one of the problems that we faced with this was that in order to get this circuit, and this is your circuit. Let me just move it out here, because your circuit uses the same capacitors both for the feedback network and the Colpitts configuration and as the frequency determining element.
Yeah.
And we really liked this circuit, so we went with it. The problem was that when we used, I think we have like 660 picofarads there. Okay. I have two 330s, right? So there's two 660s.
Yeah.
In order to get it to resonate on 40 meters, we had to put so many turns on this thing that it resulted in a
band spread,
well, very little band spread, but it resulted in another way to say that is that the oscillator would tune from like 6.8 to 7.8. Which was far more frequency that we were interested in.
Yeah.
So we did a couple of modifications. One, I split this inductor up into two. And I have a fixed inductor here and a variable inductor here. So I have it tuned so it'll only really tune the 40 meter band from 7 to 7.3.
Right.
The other thing is we changed the screw.
Okay.
It originally had a brass screw in there, but we changed to a steel screw.
Okay.
And we went with a steel screw that had a tighter pitch.
Oh, so
it's more turns.
Right.
So right now, to get across the 40 meter band, we have to do, I think, like 21 turns.
It's pretty good, you know. It's actually very nice. There's no backlash.
Nope.
And
And so this was like, and the thing about the steel screw is the physics. It's interesting because we think we're getting both effects. When you put a brass screw in there, the brass has a permeability equal to air.
Yeah.
So you're not really changing the permeability.
Right.
You're just putting shorted turns.
Shorted turns. Right.
It's called, you're just having shorted turns go in there, and that's changing the inductance of the coil.
Right.
But when you have the steel in there, you're getting two effects. You are changing the permeability, and that's pushing the frequency in one direction.
Right.
And you're putting shorter turns in there, which is pushing the frequency in the other direction. And the result is it requires more turns to get across, which is what we wanted.
Yeah.
So you could see here that when you look at our fancy, frequency readout, that to go to 7.0 down here at the CW portion, you're way down there. But then you have to make a lot of turns. You go through FT8.
Yeah.
We'll go up and listen to some SSB signals.
It's got such clear audio.
I think the speaker is a little bit of frequency restricted. But that's one of the mods we're encouraging the students to do. They could put a bigger speaker in there.
Actually, if you mounted the speaker onto the panel, it would have sounded better.
I know.
Because you'd have the baffle effect.
Yep.
And that's the band pass filter. It's a two-section band pass filter.
That we stole directly from Hans.
Right, okay.
We took the circuit from the G0 UPL site.
Okay.
And it's fine. We had a lot of trouble. Here's the audio again. Look at this. So we actually have a lot of trouble with one particular transmitter. It's a transmitter called Radio Marti, which transmits out of Greenville, North Carolina, which is fairly close by. I think it's 250 kilowatts. Okay,
wow.
And it's aimed at Cuba. Oh. So we're off the back of it. But we still get so much energy. The frequency is, sometimes it's so close to 40 meters, 7335. So if we tune up to the top end of the band, we'll start to get AM breakthrough.
Oh,
That's why we went with the diode ring.
Right.
The mixer, the diode ring. We experimented. We tried to go with a simple 2-diode mixer. And we would get a lot of AM breakthrough. But then we went with the diode ring, and it solved it. Let me hear. We should be here. Radio Marti should be fired up now in the morning. Let me see. Starting to hear it. See it?
Yeah. Okay.
Wait a second. There he is.
Yeah. That's pretty strong. It's like a local signal generator.
Spanish.
That's pretty stable as a VFO because it's very difficult to tune AM on a direct conversion.
It is. Well, I mean, and this just shows that
Yeah.
you really can't tune AM on a direct conversion receiver.
Yeah.
Even if you get it at 0 beat, the distortion is really quite apparent.
Yeah. That's because even if there's a little phase difference between the two side bands, as they're coming in, they'll either add up or subtract.
That's right.
Rapid fading.
Right. So in other words, if this was an SSB signal, like you listened to before, there's no problem.
Yeah, of course.
But this is so people often say, well, oh great, can't I take this and listen to AM broadcast?
No,
you can, but very poorly.
Yeah.
So that's what we hear here. So when we go off 0 beat on either side, like there.
Yeah.
So, but it was pretty good.
Low rumble of the
Yeah,
side bands,
yeah. But that's just above the 40 meter band.
Yeah.
But you can see we've kind of licked it.
Yeah.
It's a very strong sideband signal there.
Just cut down the gain.
There's some sort of net going on there.
Yeah. Do you get the audio transformers readily in the market, or
we found a source, and I think we got them from Mauser. Now the thing is, this was interesting. We found some audio transformers that were dubbed as 8 ohm to 1K.
Yeah. Okay.
And we found them on Amazon, and we bought them.
Okay.
And we tried them, and they worked very, very poorly.
Oh. Okay.
And then we found posts going way back to Alan Yates, VK2ZAY.
Right. Yeah.
And Alan had the same experience with these transformers, and he had done tests on them and determined that they were not.
Oh, they must have been 600 ohms, 600 ohms.
They were something different, but they were just not. Okay. So we got rid of those, and we found a source, I think it was Mauser, for these transformers. Okay. Now, a lot of people will say, don't even bother with the transformer, just get an LM386, right? But we wanted to make this an all-analog project, so we went and we got this. Okay. The other thing people would say is, even if you don't use an LM386, you can basically build your own. And this was one of the circuits that Arv Evans, who's recently become a silent key, came up with, which is a push-pull. It's basically a discrete component version of the LM386. Yeah. We rejected that also, just because it would be more complex, and it would be harder for the students to understand. We figured 3, common emitter transistors would be fine. So the simplicity was the watchword. And the other thing that drove us here, Farhan, was something you talked about when you were working on many of these rigs, and that is there are really only 4 circuits that the student has to master: the oscillator, the mixer, the filter, in this case the bandpass filter, and then the audio amplifier.
So all the 4 they built.
They built all 4. And one thing I'll say though is that, well, they built all 4, and we told them that if they mastered these 4, they would be able to understand the working of all wall radios, which was important. There's a couple things we discovered. First of all, when doing the diode ring mixer, the transformers are quite complex.
Absolutely. That's one of the reasons why we didn't go the diode mixer way.
Well, we cheated. Okay. I cheated using transformers that you had left me. When Farhan came through on a previous visit, he left me a big box of tri-filler wound toroids on FT43 material, which was perfect for this. So Dean and I, we chickened out. We said, this was like the 2nd or 3rd session with them, and we thought that having them wind tri-filler transformers in a group, in a confusing classroom would be hard. So I pulled out, we knew that we were going to build 15 of these receivers. So I pulled out 30. Then the other thing was, Dean said, yeah, but they're going to get confused in terms of the windings because yours were not color coded.
Yeah.
I think they were done by the seamstresses.
Collective.
Yeah, the women's collective. So I came up with a scheme. I said, okay, here's what I'm going to do is on each of these transformers, there's one kind of top to bottom.
Right.
I'm going to solder those together.
Okay, so you have primary and secondary.
Right.
Yeah.
And then the only others, there'll be two that'll come out that'll go to the diode ring.
Right.
And there'll be two that'll come out that'll go to the input, either the RF or the LO.
Okay, so you pull them apart.
I just wrapped them.
Oh, okay.
And so we gave the students instructions. We said, look, first come up with your PC board pattern, then solder down the common connection, either to the LO out or to the ground.
Okay.
Then take the two wires and put them to either the top or the sides of the diode ring.
Oh, okay.
And then the other two, one goes to ground and one is input. Right? And so they were able to do that, and we've had very few problems with them. There have been a couple where they put them in and they weren't careful about twisting, and there'd be a short underneath because some of them, the wires, there's not a lot of insulation there. And so we got all the diode rings to work, so that hasn't been a problem. One of the things that we learned from the project, though, is that we kind of foolishly, I wouldn't say foolishly, but we assumed that once we got all four boards built and tested, that integrating the four would be easy. Yeah. Right? Okay. And we discovered that's not really the case. You know, so I mean, we did really emphasize the point of building it by sub-circuits. Don't think of this as a mass of parts. That's the way I thought of the Herring 8.5 when I first built it, which was a mistake. So we said, look, build each section and then test it. We even in the audio amplifier, we broke it down. Build the first audio amplifier first, test it, and then build the other two. This was the most complex board. Right. This was like 14 pads and 26 components. But then the other thing we discovered was that it's not simply a matter of connecting it all together. Because sometimes, even if they've tested all components, when they put them all together, it still doesn't work. And that requires, because what will happen is they'll have jostled something. Or a connection from in one of the toroids will be to ground where it's not supposed to be. So there it does require some additional kind of troubleshooting. So we would go through with them, and this was actually one of the most instructive parts of the whole thing. The students would come to us and say, my receiver doesn't work. Right. And then we'd say, okay, let's systematically figure out why. Is the oscillator working? Yeah. The bandpass filter is usually not a problem. True. The mixer can be a problem. Sometimes if the mixer's not working, it'll pull down and prevent the RF oscillator from working. The audio amplifier is complex, but relatively easy to test.
You could just keep putting your fingertip somewhere.
Oh, thank you very much, because that's what we told them. You know, and this is part of the tribal knowledge that we were trying to share with them. We said to them a couple things. You know, when you go into a high-speed EE program at MIT, you're probably not going to get somebody who's going to say, hey, just put your finger on the input, and if it buzzes, the audio amplifier is working. But that's really all you have to do. Don't worry about getting a complex signal generator and measuring how many. Just touch it. Does it bzz, bzz, bzz? Okay. The other thing we told them that was a lot of fun was squeezing toroids and squeezing coils. We brought in some of the these great LC meters. Todd, VE7 BPO, just sent me another one.
Oh, really?
He did. So now I have two. I have one for the Dominican Republic and one for here. But we would measure, for example, in the bandpass filters, we were shooting for like 6.3 microhenries or something like that. We would measure, and sometimes the students would come up with like 5.7. And they would be, oh my God, it's 5.7. And I would say, what you need to do is just squeeze the coils. And they would look at me like I was crazy, like I was telling them to squeeze something. I said, no, squeeze the coils together. And they would squeeze it together, and they would see on the meter it go to 6.3. Perfect, boom, that would go in. But these are kind of analog kind of skills that we have to pass on. So this is one of the objectives in doing this.
Why were you putting an L match there?
Where? Where was this?
You drew up an L match here.
No, this is because the board was from a previous project.
Oh, that's
that's probably pretty. Now, there's an interesting thing about the board. When I decided to use this board, I just went to my junk box of boards, right? Okay. And you could see I marked I was going to cut it here. Right. All right. But I decided not to cut it because eventually I might want to build a little transmitter, build a transmitter back there. So I left the board, which is another lesson to teach the students. One of the great things we taught was that, the use of the Manhattan technique. You can see I've just got all pads that I glued down. I like to glue pads down. I use voluminous quantities of Gorilla super glue, and we just glue the pads down. And so the students got used to the idea that they could put the pads down. But one of the ideas that we had to introduce them was that, look, if you have an extra pad, don't worry about it. Just don't
Exactly.
And if you misplace a component and you need another pad, put it there, right? Just glue it down. And I would tell them this is sort of like freestyle home brewing, So, we think that they've gotten a lot out of the project. Now I went with a front panel. Dean's is a lot neater than mine, but I just went with a kind of a wooden front panel here. Let me move this thing up here. Oops, aim this up here. Hold on. Look at that. Loosen this thing up. There we go. I went with a wooden front panel. I just to remember that it's a TJ project, I would put the visitor pass that they gave us.
Okay.
So that's the visitor project. Yeah. But this hole through the front panel adds a little bit of mechanical stability to the screw.
Okay.
And actually, we found it to work a little bit better if it puts a little bit of downward pressure on the screw, because it prevents it from jostling around quite a bit. Yeah. But even if it jostles, gravity will do it, and it'll keep it stable, as we saw. And we have an audio frequency gain control. In some of the others that I built, I put an RF gain control also.
Okay.
Just a 10K pot.
Right. Yeah.
It's not really that necessary.
Yeah.
It helped a little bit when we were struggling with the Radio Marti problem.
And how did you source the knobs for this?
I just found them at a Hamfest.
Okay.
As a matter of fact, we found them at a Hamfest, and the guy was selling them for way too much money.
We actually used a lot of bottle caps.
That's good.
Yeah. You can just super glue the bottle cap on top of this, and some of them got these big, jar kind of bottle caps.
Yeah, it's good. That's a good way to do it. That's a beautiful way to do it. Now, have you been able to take the students out and have them listen to 40 meters?
No. I mean,
neither have we.
Yeah. It was the same problem. I mean, they did listen to the band before we started out, saying that this is what it's going to sound like.
Right.
And then we went back and built this. But unfortunately, what happened with us was that the exams came in, and these are, senior high students, and they were applying to colleges. So that's always a problem.
We face the same problems, and that especially in the second semester of the year, as they're approaching the year's end, it becomes more difficult for them to do that. But let me put this over here. We'll continue our discussion. Here, hold on. Well, no, it's okay. We'll keep it here for now while we're talking about this. But one thing we've done is that we've got like 4 or 5 of the receivers have been completed.
Okay.
But we're inside the lab. The lab is like a Faraday cage.
Oh. Okay.
And we don't have the ability to put an antenna outside.
Okay.
On one of our first visits with the receiver that you inspired, this one, I left this one there.
Okay.
Right? And this is something you could see. I left a note saying to them, look, there's Farhan explaining the receiver in Hyderabad, a quote from him about the virtues of building a direct conversion receiver, and a little, basically block diagram.
Yeah.
And I left that with them. We threw a wire out the window of the school.
Okay.
And we're able to use it as a 40-meter receiver, but it wasn't a very good antenna, and it created a lot of anxiety at the school. So it eventually just went away. It sort of evaporated. Somebody ripped it down. But what we're thinking about doing now is kind of going over and putting up an end-fed quarter wave. Okay. And that's why there's these 2 clips that you see here, right? Okay. So one connects to the input of the bandpass filter. Okay. And it's just a quarter wave of wire, right? Okay. Now, when you're using just a quarter wave, the ground is very important.
Yeah. It has to be quarter wave length.
It has to be quarter wave, or it could be just a ground. Yeah. But we think most of the students, or many of the students, are operating out of bedrooms on the 2nd or 3rd floor of a house or a townhouse or an apartment. So it would be difficult for them to get a good ground. Right. So instead, we came up with the counterpoise, just a quarter wave of wire. Okay. And Dean and I both did videos. A lot of a lot of even very seasoned hams don't believe this is true. But if you put out a quarter wave wire, and I have one up from, I actually tested this from the upstairs window in this house. You put out a quarter wave wire and you just hook it up to the input of the bandpass filter. You'll hear almost nothing. Nothing, really. It's really bad. However, when you take the counterpoise and you put it right there on that one, it's amazing. The band just opens up, and the reason is it's electrical. The signal is coming into that port, but it really has no place to go.
So
right?
It doesn't get.
It doesn't go. It doesn't go through the primary of the coil and the bandpass filter. Once you hook up the counterpoise,
So
even if you have the counterpoise laying on the floor,
it doesn't matter.
it doesn't matter. It provides. It's basically a synthetic ground, right?
Yes.
So we thought this would be a good antenna. You know, some guys had suggested a very popular antenna here now is the end-fed half wave. It's a great antenna. Don't get me wrong.
Too big.
Too complicated. You need coax.
Correct.
You need a transformer. Maybe a tuner transformer. You need a half wavelength of wire, which on 40 is 66 feet.
67 feet.
33 feet is doable because it could go out the window and to a tree or to something across the courtyard or something like that. But anyway, that's the antenna we went with.
One thing which you can try out, I don't know how strong the signals are, which is just to put a whip here. Because what happens is that this point, which is, across the coil across either of the inductors or the RF preselector, is very high impedance. So it will act as a very weak active antenna. You just put up a whip there.
I think we could try it. We could try it. It would be good. It certainly doesn't work inside the lab.
No,
so we're going to have
at
to
a window,
outside. At a window,
just about 7 or 8 feet of wire. Vertically strung out.
We're really pleased with the whole thing. And one of the things we want to do is, since most of the kids are quite kind of digital and computer oriented, there's no reason why they couldn't take this and take the audio output from this and just run it into FL Digi and watch what's going on FT8 or PSK or things like that. So that's one of the things they could do. They were oddly fascinated with CW signals coming in, but and I think almost sort of a kind of the same way you'd be fascinated at the Natural History Museum, so something ancient. SSB signals they find harder to tune. You and I do it kind of instinctively, but they will just hear this kind of monkey chatter and think something's wrong, and then not realize that you have to just point it. It's especially difficult on a direct double sideband receiver because you're going on both sides.
Slip to the other
side.
side.
Slips to the other side. And if you're on the wrong side, you're never going to be able to tune it right. But anyway, that's.
But the direct conversion receiver, it's a good compromise between something as simple as a regenerative receivers, which are almost impossible to tune, and a superhead, which is far more complicated, right?
We put, and we've submitted this to the Hackaday Prize Project under re-engineering education, and we said that we selected the direct conversion receiver because it had struck a good balance between simplicity and usability. It was sufficiently simple to be in a one-semester project, but the result would be a usable thing.
Absolutely.
And so we went with this. A receiver is a good way to start. Also, we think the students appreciated the challenge.
Right.
I was joking with you last night. I might have been telling Humera. We told them that the famous quote from John Kennedy is about why do we go to the moon? He said because we choose not to do the easy thing. We choose to do the hard thing. He said in a very Boston accent. So I put that quote up on the screen and I said, we're building this receiver because it's hard. But then I put up the kind of a corollary joke. Some guys had put it up in their workshop. He says, we're not doing this because it's easy. We're doing because we thought it would be easy. And we're finding out it's not. But I think one of the last things we're going to do with this group is probably go out somewhere on the school grounds. And just put up the same the same kind of antenna that we would have them use in the home, right? Just a quarter wave wire, 33 feet. There's so many things that we take for granted that if you've never done it, it seems alien. How do you throw a wire up into a tree, right? How do you do that? And then how do you hook up the counterpoise, things like that. So we'll do that with them. And the idea is we hope that some of the students will take the receivers home and actually use them and listen. But even if none of them do, at least they'll have built it and they'll have successfully built something.
They've learned a lot of mechanical skills. They've learned to solder. They've learned, and for us, the most important thing was that how do you translate a logical schematic to a physical manifestation, right? And that actually is a very key skill that most of the homebrewers have, and others miss it. That you have a circuit diagram which looks oddly, it's all right angles and everything is clean, to something which is as ugly as this, but it's the same thing.
Yeah.
And the correlations between the two in your mind, after probably building the first block, then it becomes natural to them, or at least semi-natural.
This was one of the most gratifying moments in the whole process, because we were trying to encourage the students to make haste slowly. In other words, be careful, but don't dawdle. Don't take a board that should be built in one session and turn it into a week-long project. No, get it done. All right. So, and to inspire a sense of urgency, we would give out prizes for whichever group finished the board first.
Okay.
So they got into this, and they got into the competitiveness of it.
Okay.
By the second or third session, we would present the schematic.
Okay.
And I saw several groups grab the schematic,
and
run to the workbench. And what they were doing is they were putting the schematic up so that they could quickly see it. You know what they were using? They had solder suckers, like little fans that were sucking the air in through a charcoal filter, but they were using the air pressure from the solder sucker to put the thing up. And I said, that might not be a good idea from the health perspective. But the great thing was that they were doing exactly what you described. They were saying, okay, here's the schematic. Let's lay out a board. How many pads do we need? Put the pads down. And then just start putting components on the board, which is a skill. For me, it was a skill that very few people have. We told them if they succeed in building a receiver, they will have done something that.
So our idea was that once you've done this, you'd be able to pick up any magazine or internet, look at a circuit diagram and say, I can do this.
That's right. Yeah.
Yeah.
All right. So we'll move on to the next one here. Let me get the cameras reoriented here a bit. Stop this. Oh, we'll keep this one the way it is. But what I want to reorient is, let me see, my tripod. This is an ancient tripod. It's going to fall over. Hold on. And then I'm going to move this camera a little bit over here. So I think we can see ourselves a little bit better. All right. So, okay. So the next thing I want to show you is another one of your creations. There's so much Farhanismo in here. But the second rig is the Microbitex. All right. This is the second
scratch build.
Huh?
It's this one is entirely scratch.
No. This one is built on your board. This is a Microbitex.
Okay.
And actually, this is one that was purchased originally by another great friend of the Sosmo podcast, Rogier, Papa Alpha 1 Zulu. Okay. And for some reason, he couldn't work with it, and he sent it to me. Okay. So Farhan, I admit it, I have become, this is like an orphanage for BITXs. I have many BITXs around here, many BITX 40s, many Microbitexes, but I operate an orphanage for BITXs. So it's useful for me because this is the second Microbitex that I'm working on. Okay. The first one we have over there, and that's the one I've been taking to the Dominican Republic. Okay. And I've used it several times. Mm-hmm. On the last trip, I discovered that I tried to put it on 10 meters, and I discovered that the power out on 10 was way low. Right. So I started consulting the internet, and I found Allison's. Right.
She's brilliant.
Listen, Allison is so brilliant, KB1 GMX, that whatever she says, I don't question it. Yeah. I just do it, okay? Yeah. So Allison recommended, and I'll come over here. We can come over this way here. Okay. So I'll open it up. But I like these boxes. I get them from Amazon. What boxes
are these?
These are boxes from, Amazon sells them. They're called basswood boxes. Okay. I'm terrible at metal bashing. Mm-hmm. I hate working with metal. So I get these boxes, and then I convert them into shielding, right? So I get some of this tape that you can get from Home Depot, and I just line it on the inside. This gives us the shielding that's required. Right. And when you're operating mobile or portable, it's especially important because often the dipole is right above your head. Right. So if you don't have some shielding, it's going to get in there, and it's going to get RF feedback, and guys are going to complain. So anyway, here's the board.
Okay.
All right. Now, a couple things I had to do. I have a broadcast interference problem here, big time.
So you have a BCI, right?
Yeah, I have a station down the road, WFAX.
Okay.
That broadcasts during the day. It transmits at 5 kW on vertical antenna 1 mile away.
Man.
And it produces a massive signal that overwhelms everything. So I built a little BCI filter here.
Okay.
That's got it's basically a high pass filter.
Right.
With a cutoff at 1.7 megahertz.
Okay.
So the whole broadcast band gets knocked down. If I don't have that filter in there, it's useless.
Right. Okay.
If I have the filter in there, everything is fine. So then I started doing the mods that Allison recommended. Okay. First, she recommended changing all these 2N3904s to 2N2222A. So I got those. Then she also recommended running them at higher current.
Right.
So instead of 22 ohms in the emitter, she recommended 11.
11, okay.
So she said you could do this by taking another 22 ohm
and put this in parallel
on top.
Yeah.
So I did that.
Okay.
But then Lex in the Netherlands told me that he found that this made the transistors run hot.
Yeah.
And I put my finger on this. I did the Doug DeMoor finger test. Okay. The Doug DeMoor said that if you wanted to see if a component was running too hot, just put your finger on it.
Right.
And if it causes pain, it's too hot. I mean, look, I have a more sophisticated thermometer, right? I can aim the laser beam at it to tell me exactly what the temperature is. But I was using the Doug DeMoor method. So then I went out and I bought heat sinks for the 2018 can.
Okay.
And I got them on eBay. They wouldn't fit, so I clipped them off a little bit. So now they all got their own heat sinks. Those are in there. And this makes it really run very, very well. It's nice. Okay. I managed to blow up 2 Arduino boards. So Mark sent me a replacement Arduino board, and I got some replacement Arduino boards from Sunil in Uttar Pradesh. So now this thing it's working, and it works really well.
And are the PAs still IRF 510s?
Yes.
Okay.
Yes.
And how much output do you get out of this?
Okay, so I tested it, and I had been getting on 10 meters. But look, first let me say this. I think when Allison's mods were really designed to do 2 things, I think. Okay. One was to increase the output at the higher frequencies on 10 meters, and it did that. But the other thing she wanted to do is she wanted to even out the output. So it would make it easier to use with an amplifier. So you wouldn't want to have a situation where the thing was putting out 10 watts on 75 and 2 watts on 10. So she was trying to level them. Right. And I think she's succeeded to an extent with that. And hers is different because she usually runs the IRF 510s at 24 volts. Yeah. I'm still running them at 12 because I'm chicken. Yeah. But I actually tried changing the IRF 510s to the RD06 or the RD16.
16 SHF ones.
Yeah, I think I went to the RD06. Okay. And it didn't help. Okay. Allison makes the point that it really doesn't make any sense to replace these if you're not going to increase the drive level. Right. Like you could replace them, but you'll get a marginal improvement in power out, but it's not enough for people to notice. True. So I just left the IRF 510s in there. Also, I know you designed this for the use with the IRF 510s, and I found that it was much more stable with the IRF 510s. If I put the other transistors in there, I had instability problems. Right. So I kept the IRF 510s in there. Let me just turn it on. We're doing this before. Here, put this here. Let's see, what band am I on? I'm on. Let's change the band. And I have it on. The mode is USB, but I haven't changed. I haven't changed the BFO, so let's leave it that way.
Yeah. That's nice.
It's really nice.
Yeah, good tone.
Oh, but I have it on USB, so we got to change the mode. We got to go to LSB. Yeah.
I've even forgotten how this works.
Yeah.
I haven't been using this user interface for a long time.
KD8 CEC.
Yeah.
So go up. and I'm moving at 1,000.
Tried to do by least amount that I owe, and I got away pretty well this year. Yeah, playing off is not a bad thing, but it's still real money.
It sounds really good.
Yeah.
I'd rather have the money.
This is another knob that I picked up at the Hamfest.
Zulu Mike, we've got you recognized. Anyone else?
Wow.
And this is just off the dipole.
Okay, the Mobile, I think it's a K4, it's hard copy. Here, try again.
That's a pretty powerful signal.
No, it's really nice.
Okay, I need a relay.
Kilowatt 4, Quebec, United.
Anyway,
what was the last
so this,
letter?
I'm gonna. You can see it works quite well. I'm really happy with it. It's really nice.
Why don't you? I mean, there's space in it. Drop a battery into it.
I could. I had a battery in it, and the other thing that I did was on this other one. Let me show you. I think I might have showed you this before. But I'll bring it over here so we can put it on camera. This is the other, my original Microbitex.
Okay.
Now here, I foolishly didn't put. Here I have the heat sinks hanging off the back.
Yeah.
I didn't do that with this one.
Okay.
So instead I put a fan up here, and I put
Okay.
a hole so there's some airflow. It's kind of hokey, but this one here, you can see.
Yeah.
Let me see. I'll put this here so people can see it. Let's
Yeah,
put it on one
okay.
top here. So this is the other one.
Okay.
This one I have an internal speaker.
Right.
It's a V3 board with software version 1.2. But look here, you can see I put in a
CW filter.
CW filter.
Okay.
So this flips on the CW filter.
Okay.
And this is all set so that if I'm listening to side tone, which is set at about 650 hertz,
Right.
and this allows me to zero beat a lot better.
Oh,
a lot
okay,
better.
okay,
So
okay.
anyway, I have that in there. So I might do something, but I don't really use it that much on CW. Plus, I think one of them is going to stay here, and one of them is going to go to the Dominican Republic.
Okay.
And I'm not really that into sort of portable operation.
Right.
I just
Yeah,
don't do
yeah,
it that much.
yeah.
But anyway, so you do have some space here. Interesting thing, I had to put this relay. You asked me about this relay before.
Right. Yes.
Why?
Correct.
The relay is to control the external amplifier.
Oh,
to key
okay.
it.
Okay.
Now,
okay.
one thing that was interesting, you would think that you could just take the push-to-talk control that
Right.
goes to ground and hook it here, right, and not need the relay.
Yeah, that's
It
not,
didn't work.
Yeah, it didn't work because that goes to the Arduino, right?
That's right.
Yeah, yeah, yeah.
And when I hooked it up, it would stay stuck in the transmit
Right.
mode. So now I just put a relay in there, and all the relay does is that when I hit the push to talk, it actuates the relay,
Okay.
and that relay is what takes it
is
to
what
ground,
takes it. Okay.
right? So this way it works. It works this way. It didn't work the other way, but now I can use it with an external amplifier. Anyway, that's that project. I think we already talked about this one. Let me make sure we're on camera.
Yeah.
This was the inspirational DC receiver,
Receiver.
that originally we showed to the students and sparked a little bit of interest. The story of,
What knob is this? This is a volume control.
oh yeah, this I put in, actually in this one it's an RF gain control.
Okay.
There's no audio
There's no
gain,
audio.
no audio
Okay.
gain control. You could do it all with RF
Right,
gain,
right.
which is another way of doing it. But that's the way I did it.
That's an interesting way to mount the audio jack. I
just
always
glue it
have
down.
problems, when constructing it breadboard style. That the
Yeah.
audio jack always hangs out.
Well, actually, this receiver was something that I just cobbled together, and it's probably a terrible design, but it's got a 2-diode kind of Doug DeMaw mixer. It has a little RF amplifier, which is probably not necessary on 40 meters either.
right.
And then it's got kind of a Hearing Aid 5, like 1, 2. No. This has the Arv Evans kind of.
Okay.
Look, it's got
Audio
push
amplifier.
pull.
Yeah, push pull. With
2 N3904 and a 2 N3906 with a
biased.
2 diode to bias it. So this is another Arv Evans product here, and that's why I have no transformer. So that's the way I did it. But then when I looked at it, first of all, I discovered that my ceramic resonator VFO wasn't as stable as I had hoped it to be. Even though this is an embarrassment. This was on the front page of Sprat. And then so I scrapped it and built a separate VFO using this Galaxy G5 mechanism, anti-backlash mechanism.
Right.
This is one of those that Pete just said I should get, and I got it. And so I'm using it here. But it works, it's okay, but it doesn't work nearly as well as one that we were more thoughtful about the design with. But Farhan, you also asked about glue sticks.
The glue sticks, yeah.
And so I built this is just a kind of an Arv Evans kind of audio amplifier,
okay.
but I had at different points your whole PTO built up here, and I just built this mount just to show you how or to demonstrate to myself how easy it would be to do kind of a PTO using a glue stick.
Yeah.
So I just took 2 pieces of wood, super glued them down to the board, and cut holes with a hole cutter that was about the right size for the glue stick. Put the glue stick in there. And then what inside this thing, let me see if I can take this off. It might be difficult to get off.
No,
I don't want to get it off. But I just removed the glue.
Okay.
And inside, I just super glued a chunk of ferrite material.
Okay.
All right. So as you turn this, the ferrite
the
material rides along.
Okay.
And it changes the inductance of the coil, and you could tune it that way. It's a super simple mechanism.
Yeah.
I mean, people shriek with horror when they see this thing because it's so far from the SDR rig, but people have picked it up, and Nick M0NTV has no pun intended. He's become a major adherent to the glue stick method, and he's got a whole bunch of glue sticks going. So we put the glue stick in.
You know, the thing is with it, whether you use the glue stick with such an analog and very organic stuff, or that the maths is the same, right?
Right. It's the same thing. Yeah. The other thing I wanted to show you. Let me make sure this is on the camera here. Let me see. Oh, we're good. We're good. All right. So this is something that popped up recently, and then we've been discussing. The Franklin oscillator. All right. So this is a circuit that a guy in our radio club, Lee Garlock, who you might meet today, he started talking about using the Franklin oscillator. And the Franklin oscillator, there's a couple of distinctive features of it. One, it uses 2 transistors, right? And the 2 transistors provide the 360-degree feedback path. So one of them inverts. Then the other one inverts again. So instead of like in a Colpitts or a Hartley circuit where you're using the resonant frequency, the resonant circuit to also get you the phase shift required. Here the phase shift is required by these is done by these 2 transistors. So actually you have quite a bit of in phase input to output signal going there. But then you very lightly couple the LC circuit. And the result is that there's a lot of feedback coming around, but everything except the frequency of the LC circuit gets shifted to ground. But this presents a high impedance at the resonant frequency because it's a parallel LC circuit. The thing about it is, people claim that it's extremely stable at higher HF frequencies. And when I first read this, I said, when Lee was telling us about this, I said, how could that be? I have never seen it. I haven't seen it in any of the books or anything else. But I built one, and after I watched a video by Mike, WU2D, he did a video. And I said, wow, that is a really fantastic VFO. He had it built so it would produce up to 21 megahertz.
Wow.
And it was really stable at 21 megahertz with no frequency doubling, just at 21 megahertz, rock stable.
Straight.
So I said, I want to have one of those. So I built it here on another little bit of one of these.
And how stable is this?
It's really stable.
Oh, really?
Let's see. Hold on, this is the test. So we're going to take this.
Do you maintain a logbook of these experiments where you?
You know, I know. I try.
Because we could have seen the circuit diagram.
I know. I have it here somewhere, but it's kind of hard to find. But we'll do it right now. We'll just put it on here. So I got it powered up, and I'll take the scope. Go to ground. There's a ground connection right there. I've got a ground connection over here. And then the output, I'll just put it on the collector. So look, the frequency of this right now.
Oh man, it's already stable.
Hold on.
It's within 100 hertz right now.
And what's the frequency? See the frequency on the counter? It's almost 14 megahertz.
We just need to stay away from it so that our bodies don't. Oh wow, that is pretty stable.
I mean, and you can see it's just moments ago powered up. It's sitting on the desk. It's not covered by anything.
Yeah.
Air currents are blowing over it. It's heating up. But this is what we see with the Franklin. And you could even look. It's variable. So I moved it up to 14.4 megahertz. Yeah. So, I mean, and look, you can see it's constructed. The coil is nothing but, there's my standard coat hanger cardboard tube. An idea that I got from you, by the way, because you took the kids in Hyderabad to McDonald's and even straw. Anyway, so I make them that way, but I've kind of broken it up. These are the active components, and this is the passive components, and the coupling is by very small capacitors. I have little capacitors in here that are at 1 picofarad.
And what transistors are these? Are these FETs?
No, these are 2N3904s.
Oh, really?
Yeah.
Wow.
I talked to somebody about this who knows, and they said you'd get better results with FETs.
Yeah.
So I might try it again with FETs.
The Q here will be determined by how lightly you load it. And because FETs have almost infinite input impedance.
Yeah, we recently saw another circuit using an FET, and one of the things that surprised me was I didn't see going to the base on these. You have a 1.5 PF. Right. On the circuit that we saw with FETs, the builder had omitted that 1.5 PF going to the gate because in effect there's a capacitor in there, so he didn't even really need it. Yeah. But look, it's still at 14.431. Yeah. Look at that. Yeah.
It's pretty dead stable. It's just.
I actually built, when I was testing this thing, I built something that Wes recommended. Wes recommended building kind of a temperature chamber. Yeah. So one of the things we do is we get these. We have a food service here called Hello Fresh. Okay. They will send you by a courier
in a foam box.
A foam box. The box is well insulated and it's the right size. Yeah. So I took one and I put a light bulb inside it. Okay. And I have a temperature sensor. Look, these like cheap from China DMMs have a temperature sensor that you can hook it up. Okay. So I have this reading the temperature inside the box. And so, and I have a counter. This counter, usually I'll watch on this counter, watching the output. Okay. And then I'll turn on the light bulb. And as I watch this thing increase, I can see the change in frequency. Now, of course, it does change because you're heating up this element, right? So but you could test sort of relative stability and compare one to a Colpitts circuit. So I was kind of doing that, playing around with that. But
when we were building, the stuff for the satellites, so I'd actually regularly put my RF circuits into the fridge. Yeah. And I could actually monitor them outside because,
Yeah, you got inside. Well, one of the things that you hear about VFOs, and there's a lot of lore about VFOs. What you have to do to make the VFO stable. What you have to do. And a lot of people say, it has to be in a hermetically sealed box. Right. So I actually went out and got a hermetically sealed box. Look at this thing. Man. Look at this. Yeah. Look, it's even got, insulators. So when you put it in there, you could build it in there. Yeah. But the truth is, I've never really had to use it. I suppose it's better because it will be certainly much more impervious to outside temperature changes. Yeah. Yeah. But the other problem is you've got the active elements in there, in the same chamber,
heating it up. Yeah.
So it's good that when it heats up, it'll reach thermal equilibrium, but it's still heating in it. Yeah. So you might want to.
True.
I don't know.
For the sBITX, we were using this real-time clock, which said that there was a temperature compensated oscillator inside it. And what I realized is that it doesn't hold the temperature perfectly still, but rather it has calibrated the amount of drift that the oscillator will have at different temperatures, and there's a temperature sensor, and it automatically adjusts the divide ratio to get the correct frequency.
This is happening in the sBITX?
Of the real-time clock in the sBITX.
Is that based on an SI5351?
No. This is the real-time clock chip in it, the DS3231.
Wow.
So when I was reading the data sheet, I I mean, I was thinking that this is going to consume a lot of power if it's going to be a thermally compensated oscillator. But what they meant was not that it will stay on the same frequency, but the drift is calibrated. So, the chip adjusts the divide ratio to get the 1 second pulse at different temperatures inside.
Wow. Again, a degree of sophistication that goes way beyond.
Yes.
Where it's still at 14.4308.
It usually takes about 15-20 minutes for the
the thing to stabilize.
And one of the things that you could do with these is, because they hardly consume a couple of milliamps, always keep the VFO running.
I know.
There's no way. There's no reason to not do that.
No, and I've had that situation. As a matter of fact, this frequency counter that I have here, it's built around an oscillator at 3.579.
Okay.
And what I discovered, and it's in an oven.
Oh. Okay.
Anytime it's plugged in, that oven is running.
Oh.
It's on. So even though the counter is off, it's plugged in. Actually, this created a problem one time where I was doing some tests around the shack and I started detecting very strong signals at 3.579. It was this thing, and I said, but it's off. But then I said, wait a second, it's plugged in. The oven is on.
So that's one difference between the sBITX and the Microbitex. And both of them use SI5351s, right? But here, people have had a lot of problem calibrating the thing to get on spot. Now that uses a temperature compensated crystal oscillator, which I thought that would cost quite a lot of money. But you get these 25, 10 megahertz crystal oscillators, which are temperature compensated for just about $1. So you drop that into an SI5351 and you bang on the frequency. You don't even have to bother with calibration after that.
Yeah, that's fantastic. Yeah.
Just for $1, just imagine that, right? You get it. I mean, earlier the temperature compensated crystal oscillators would be probably the size of this. Right?
Yeah.
And now this is, you can hardly see it. It's the size of an SMD crystal.
Well, when you talk about the size of components, one of the things that Allison recommended, and I don't think I talked about this inside the Microbitex, was the preamplifier transistor that you had in there. I think you had a 2N3904 surface mount. Right. She said change that to a BFR 106.
Yeah. That's what the Microbitex is used now.
Yeah. So I used the BFR 106 that Allison was quite taken with.
Yeah.
But the problem was that it's really small, and I'm not really good at surface mount. Right. So right around this time, our friend out in Portland, Todd K7TFC, he's got a company called MostlyDIYRF, and he put these
transistors
onto little boards. The boards are about the size of your pinky fingernail, but that's significantly bigger than the device itself. So the first one that I did, I used his board.
Okay.
But on the second one, I decided to live dangerously. Okay. And I took it with the soldering iron and using my limited surface mount techniques, managed to get a BFR 106 in there without the board. I just put it in there.
I mean, with SMD, it's just starting trouble. You're sort of a little afraid. It's like using the valves, right? So, but once you do it, then you get the hang of it, then, it becomes pretty much simple.
It becomes easier. But
actually,
let's talk about this one.
Yeah.
Oh yeah,